Uh, who's going to help me write the electron configuration for time column 73? All right, Ryan.
1s2,
1s2,
2s2,
2s2,
sorry,
2p6,
3s2,
3s2,
3p,
3p6.
hold on.
I'm going to continue. All right, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then what?
And then 4f14.
Very good. 4f14, and then what?
Oh yeah, wait, what is it? Oh yeah,
5d3. All right. So if you were to write the noble gas configuration, where would you start? Xenon. So xenon accounts up until this point. Is that right? And then it's 6s2, 4f14, 5d3. Everybody good? Everybody good? If in case you get confused, you have these notes of how to go back to D. Everybody okay? Alright. So S orbital is a sphere, right? It's spherical. I can only draw a circle. P orbital is a dumbbell. Is that right? It's a dumbbell. Right? Alright, that's a dumbbell. D orbital is a flower petal. And you're not going to do F. Okay? So this is the orbital diagram. Guys, orbital diagram is boxes and arrows. Okay? So kids would think that if I were to write the noble gas configuration of chromium, they would think that it is argon 4s2 3d4 is what they would think it is. Is that correct? But it is an exception. Now, what are exceptions? So if you actually look at your notes from the previous class, you will have a picture that shows the different circles and the energy level. Is that right? Do you have that picture? Not this one, guys. It was in your notes, like the one here. Can I hold it up? This one. This one. Do you see this picture? So please note that the energy difference between 1 and 2 is really wide. Is that right? There is a significant energy difference between 2s and 2p also. But let's come into 4s and 3p. How much different is the energy level? Very, very small. Do you see that? The energy difference between, so 1s is way below, and then it's 2s, it's 2p, it's 3s, it's 3p, then it's 4s. 3d is pretty close, very close to 4s. Is that right? And then you have the 4p. Since this energy difference is really, really small, are you with me? For some reason, in such elements, scientists have noticed that one electron will shift from 4s to 3d, and it becomes 4s1 3d5. Now, how many total electrons can go into D? A total of 10. Is that right? What is half of 10? 5. For some reason, if elements borrow that electron and have a half-filled configuration, then they are found to be more stable. They somehow seek that stability. Alright? It's what we see in nature. Okay? And we are trying to give it a reason. It gives the atom more stability. So the electron configuration for chromium is 4s1 3d5 and not 4s2 3d4. And that is the orbital diagram. Does that make sense? So, when you follow a pattern, did I say last class also that some elements will break the pattern? Is that right? So, there are many elements that break the pattern in D, especially in F. We are not going to go into all the different exceptions and why they happen. We are only going to study one exception, that is the elements that are D4. Are you with me? What will the D4 elements try to become? D5. Because they can borrow that one electron from 4f. Is it making sense? Similarly, D9 elements will also become what? When you write the electron configuration, they'll become D10. They'll take one from the 4s and they will become half filled or fully filled. Does that make sense? D10 is fully filled. So this is the half filled and this is the fully filled. And somehow when they're half filled or fully filled, they become more stable. So if I were to write the electron configuration of copper, can somebody help me write the electron configuration of copper in its abbreviated form? Luke, you want to try? Okay. I'll start with which noble gas?
Argon.
Argon. And then it is 4s 1 3d10. Is it making sense? Are you understanding? Alright? The one electron gets shifted. Alright? Molybdenum will again have an exception. Does anybody want to try molybdenums? Alright, Peter?
KR.
KR. Yes?
MO, 5S2 or S1,
5s1,
and then 4D5.
4d5. Alright? Is mercury an exception? No, mercury is not. So anybody wants to give me the electron configuration for mercury? Yes, John? Xenon.
6S squared.
6s2. Yes, it is. I agree. I didn't object. Only your friends are laughing at you. I don't know why they are laughing at you also. He's right. It's square. You can say it the way he wants it. Doesn't make a difference. Yes. Ah, very good. Look at the bright kid. What F?
4F.
Very good. 4F. 14.
And then 5B 10.
10. Very good. He didn't forget the 4F14. That is impressive. Alright? Now, so the next thing we need to know is how to write the electron configuration for ions. Alright? Cl, we know, has how many? 17 protons. Is that right? In a neutral atom, it will have 17 electrons. Is that right? But when it becomes Cl minus, what is the number of electrons it has? 18. Now you have to account for 18 electrons. So what is Cl minus's electron configuration? What will it be? Who would like to tell me what the electron configuration for Cl minus is? Anybody in class? Who volunteers? Nora? Come on, you know electron configurations. Try, come on, what is it? 1s2, 2s2, 2p6, 3s2, then what? It gained an electron. So where will it end? 3p6. Does it make sense? Which element's electron configuration does it resemble?
Argon.
It resembles argon. But why is Cl minus not argon?
17 protons.
the number of protons in Cl minus is still 17. All right, let's move on. So what is iron's electron configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d what?
You know this off the top of your head?
What is iron? What is iron, guys? 3d 6?
It's not in.
Okay. Now you are trying to remove 2 electrons from iron. Alright? Which 2 electrons will you remove? So this is important. Anissa, I'll just take your question in a minute. Now remember, 4s is a sphere. Correct? Are you with me? Let's say that is 4s, and then 3d is like a flower petal. Is that right? Are you with me? So kind of, how do you remove an electron? You provide energy and the electron should get removed. Are you with me? That's how electrons get pulled out from atoms. Now, where and how is it easier to remove an electron? When you're trying to go grab an electron and remove it, are you more likely to access the electron in a sphere or in a very narrow region? Where is the electron more easy to pull out from? From the sphere. Is that right? Does that make sense? Therefore, when transition elements make ions, all right, the electron usually gets pulled from where? From the s orbital because of its shape. Does that make sense? So when I make iron plus 2, 2 electrons get knocked out from which orbital? From the 4s. So what is the remaining electron configuration of iron? What did I knock out? The 2 electrons from the 4s. It's no longer there. But if you want to remove a 3rd electron, isn't that why transition metals need a Roman numeral? They're capable of losing the electron. Is that right? Sometimes, when I'm trying to grab, hey, I can grab from the D too. Is that also possible? Yes or no? That's also there. So that also sometimes gets knocked off. 2p6, 3s2, 3p6, that's 3d5. I've lost an electron from D also. And guess what? When D becomes D5, iron actually likes it. Why does it like to be D5? Half filled. Yes or no? So what are the 2 types of electrons that iron will give out? It will give out 2 or 3. And it makes different types of compounds depending on what is the energy release during the reaction. Does it make sense? That's why it's capable of making multiple types of compounds. Yes, John, what is the question? That's the outermost energy orbital. Is that right? Find out. The distance from the nucleus or the orbitals or their energy levels. Did we do this before? Right? 1s is close to the nucleus, 4s is far away from the nucleus. Correct? Yes? Yes or no? John, you're not saying anything. Is it making sense? Did Joanna explain? It made sense? Because those are the last 2. Is that right? So why don't you pick out from D? Why do you choose from S when you go to D orbitals? All transition metal elements. All of the transition metal elements will lose their electrons from where? From the S orbital. Okay? And then if there is a need, they'll lose from D. Alright, you may write this down. All transition metals
Oh, and then you put the remainder opposite.
will lose electrons. No, that's wrong. LOSE will lose electrons from d s orbitals. Will lose electrons from s orbital first, and then if there is a need, they'll lose it from d. Are we good?
Sort of.
You always look from the last S orbital.
The last s orbital. Let's write last s orbital, because that's the outermost. Yes, Brandon?
Do you ever lose electrons from P?
No. The P is so much more inside the energy level that transition metals won't lose from P. Transition metals are nowhere near P. Non-metals are near P. Non-metals will gain into P. Correct? Metals will always lose. These are all metals. Non-metals will gain. Remember, metals are losers. We did that last unit.
So in the other one, we did like the.
Chlorine minus, that was a non-metal.
So we gave it from.
It will go into the p orbital.
So always.
Yeah, most of the non-metals have p, so that will always go into the p orbital. Yes, Sam?
So say, this probably will never happen, but could it be like iron plus 9?
No. No. So you have to look into the math of what is the element coming in trying to pull its electron out. Remember, one is giving, one is taking. It doesn't happen in isolation. Is that right? So when one is trying to pull from this, and this one is trying to lose, the energy has to kind of match. Does that make sense? You have to have the energy to pull the electron out. If you don't have the energy, will you be able to constantly pull electrons out? We can't do that, so it doesn't happen. Okay? Let's write silver's electron configuration. Let's write the noble gas configuration for silver. What is it? Krypton. What is it?
5s2.
Silver is an exception. So what is the electron configuration? 5s1, 3d, 4d10. Isn't it an exception? All right? Okay, the Y comes from how it's found in nature. And why? It's because it gives it more stability. The D is fully filled and it gives it stability. Are you with me? Now you're trying to form a silver ion. Where will the electron come from? The S. How many electrons are there in S? 1. So silver plus is Kr 4d10. Why the heck doesn't silver form a +2 ion?
Because it only does it's not very hot ion.
Well, it could pull out one from D. Why the heck it does not give one from D?
Because it's
It's stable, it's fully filled. What is the only charge silver has among the transition metals? +1. There isn't any element that has the strength to disturb its fully filled electron configuration. There are no compounds of silver that have silver as +2. Well, silver is not 4d9. It's so desperately already taking out from the S. Is that right?
So if something fills up
It is difficult. That's what we see with elements in nature. Okay. Calcium's electron configuration. Argon 4s2. What will be calcium +2? We can't write Ar. So we'll have to write neon. You can't write a noble gas as its own electron configuration. So it will be neon 3s2 3p 6. The 6 plus 2 is an 8 outside octet rule. Will ever calcium give 1 more? Will calcium ever become 3 plus? Why doesn't calcium like to be 1 plus? Because then it doesn't get the 8. So what is calcium in all its elements? It's always plus 2. Do you see why main block elements always have a fixed charge, whereas transition block elements vary in their charges? Does it make sense? Yes. But then why are there exceptions among transition metals? Is that right? Yeah.
But you can't just say it's argon.
Yeah, you can't say. You just can't put square brackets and say it's argon. You can't write a noble gas as its own electron configuration. Because to somebody who's trying to understand what you're trying to explain, I guess the meaning doesn't make sense unless you write out those S and P, and then it means, oh, you're communicating about electron configurations.
What if, say, the element you're trying to electron configure is a noble gas?
You can't put these square brackets. You have to choose the previous noble gas and then continue. Yes.
So if they were to give you, like if someone were to ask you that, how would you differentiate from calcium plus 2 and actual argon?
Actual argon? Yeah, that they have to actually say what is the element and what is the electron configuration. Otherwise you don't. Okay? So what does the word isoelectronic means? Same number of electrons. It also means the same as the same electron configuration. Do all isoelectronic atoms and ions have the same electron configuration?
No. Yes.
Okay.
Maybe.
So say you're looking at calcium. Which is the neutral element that is isoelectronic with calcium? 2 plus. It is argon. Alright? So let's come to what is N notation. Suppose I want to write the electron configuration for hydrogen. It is 1s1. Lithium is 1s2, 2s1. Sodium is 1s2, 2s2, 2p6, 3s1. Alright? What is the last and final electron configuration? 1s1, 2s1, 3s1. What do you say it's for potassium? 4s1. Therefore, instead of writing 1, 2, 3, 4, can we give it a number n? Where n can be 1, 2, 3, 4. So the N notation for alkali metals is NS1. What do you think is the N notation for alkali earth metals? NS2. What do you think it is for group 13? You have to include the N also. It's NS2NP1. What do you think it's for group 14? NS2NP2. What do you think it will be for group 4? NS2 and minus 1 D2. Does it make sense?
No.
Don't we fill in the D? Look at group 4. Titanium, zirconium, hafnium are in group 4. N just means a number 1, 2, 3, 4. Alright? Group 4.
Why is it
Because you, after 4s, you fill 3D. Don't you fill one number less? Oh, inch. Yes?
What if you have to put
Huh?
what if you just
F and minus 2. F, whatever. Okay? Alright. Okay, I'm going to move on. Guys, I'm going to do quantum numbers now. Can you go to this worksheet that you got from last class? Go to quantum number worksheet from last class. Guys, go to quantum numbers from last class. Why is everybody's brain getting fried?
I don't understand.
What do you not understand?
Where does n come in?
N is just a general number for 1, 2, 4.
Then
N is just a
why
number.
is the 4 written that way?
Okay. Let's look at quantum numbers.
I don't know why my kids.
I'll let you go and do homework. Guys, gone are those days when you were in middle school, the teacher taught, and that was the end of it. And you understood everything. You didn't have to do any homework at home. You were just having a fun time. This is high school. Alright? You have to go home and study. Okay. Alright. I'm going to write, guys, I'm going to write a few things and we are going to see what it is. Alright? So I write my electron configuration as 1s2. Do we generally start filling out 1s2? Is that right?
Yeah.
And then I do 2s2 and then I do 2p6. Alright? Then I do 3s2, 3p6. Well, I do fill out the 4s next, but I do have a 3d10. Yes or no? I do have in the principal quantum, in the number 3, I have the sp and the d. Is that right? And in the principal quantum number 4, I have 4s2, 4p6, 4d10, and I have 4f14. Yes or no? Remember we said that the electron is both a wave and a particle, and Schrödinger gave the wave equation, and we solved the wave equation to find out where is this probable location of the electron around the nucleus. Did we talk about that? That's the origin of the SPDF. Is that right? Now we are not actually going to look at the equation or how it is being solved, but we are just going to look at the solution of the equation and try and understand it. Alright? That is the understanding of quantum numbers. Now, so we generally, when we write electron configuration, we write 1, we write 2 before the orbital that it's going to fill up. Is that right? So what do these numbers, this 1, this 2, this 3, is actually known as the principal quantum number. What is that known as? These numbers are known as the principal quantum number. Alright? And what do principal quantum numbers indicate? Indicates the distance or energy level an electron is on. Does that make sense? If n is 1, it's closer to the nucleus. N is 2, it's further away from the nucleus. Yes or no? N is 3, it's even further away. Yes or no? Alright. So, it resembles something like the orbit, even though orbit is not an orbital. Do you agree? Kind of indicates the distance. Right? Now, what are the values n can have? 1, 2. They are natural numbers, not whole numbers. There's no 0 for n. Is that right?
You can have any number.
1, 2, 3, 4.
It could be 5 of them.
It's a possibility.
But it could be 500.
Yes, theoretically, yes.
A million.
But we don't even have elements that fill in principal quantum number 7 completely. In theory, yes, John, that's the next rock star there, is the central one. Yes, they are finding newer elements. And John wants to be the next rock star, by all means. Be really excited about chemistry. Now, energy levels correspond to periods on the periodic table. Yes or no?
Go struggle together.
Okay. After writing one or two, we write an alphabet.
Alphabet.
Is that right? SP. What does that alphabet actually mean? It is called the angular momentum quantum number.
Dang, how'd you get that?
All right? They are called the angular momentum quantum number, and they are indicated by the alphabet L. Principal quantum number is indicated by the alphabet N. SPDF is the angular momentum quantum number. All right? Now, if you have value of N, what are the values of N? 1, 2, 3, 4. So for now, let's just have N as 1, 2, 3, 4. So on. Now, what are possible L values for a given value of N? L can go from 0 to N minus 1. What are the possible values of L? It can go from 0 to N minus 1.
Isn't the angular momentum quantum number a letter?
Yes, I'll tell you what it is, okay? It indicates the shape or position, shape or size. Let's say shape or size. Shape or size of an orbital an electron is. There are 4 types of sublevels. What are those 4 sublevels? SPDF. And now, well, you have to remember, where do these shapes come from? From the solution of the equation. Is that right? And you're just looking at the final solution. L is restricted by N. If N is 1, L is 1 minus 1, which is equal to what? 0. If N is 2, L is 2 minus 1, which is, well, let's do 2 minus 1. So that is 1. It can also be 0 because it varies from 0 to N minus 1. If N is 3, what are possible L values? 0, 1, 2. Are you with me? If N is 4, what are the possible values? 1, 0, 1, 2. No 4. 4 minus 1. So it's only 3. So, at the first energy level, do you have L equals 0? Which means we have a 1s orbital, correct? At the second energy level, you have L equals 0 and 1, correct? Which means you have the 2s and the 2p. At n equals 3, you have 0, 1, 2, which means there is a 3s, there is a 3p, and there is a 3d. Correct? For n equals 0, you have the 4s, 4p, 4d, 4f. Are you with me? Those are the possible solutions. So, what is the value of L for an s orbital?
0.
The value of L is always 0. What is the value of L for a p orbital? It's always 1. What is the value of D, value of L for a d orbital? 2. And for an f it is 3. Energy levels can have sublevels 0 to n minus 1. So what are the energy levels 2 can have? 0 and 1, or S and P. Does that make sense? 0 and 1 or S and P. Okay. The next quantum number is ML. What is the next quantum number? ML. M subscript L. Now, L depends on N. ML depends on L. So ML can vary from minus L to 0 to plus L. Are you with me? Okay? So now, in the first case, L equals 0. There is no minus 0 plus 0. So how many boxes do you draw for S? 1 box.
Why do we have boxes?
Boxes means the shape of an S is a sphere. Is that right? And we draw how many boxes for it? 1. Is that right? ML, when L is 0, ML is 0. When L equals 0, you have the 2S and it's going to be a sphere or a box. But when L equals 1, are you with me? What are the possible values? It can be minus 1, 0, plus 1. Yes or no? Those are the 3p orbitals. That is oriented along the x, y, and z axis. Alright? So you have the 3s, which is 1 box. You have the 3p, which is minus 1, 0, plus 1, which is 3 boxes, or the orientation of the dumbbells. When L equals 2, what are the possible values of ML? Minus 2, minus 1, 0, plus 1, plus 2. How many boxes do you draw for D? And why do you draw them? How many different orbitals of D exist? 5. Where is that coming from? From a solution to this equation. Okay? So the magnetic quantum number indicates how many orbitals are on a sublevel. Specifically, which one an electron is in. Each orbital can hold how many electrons? 2. What are the possible values of ML? It can range from minus L to 0 to plus L. For sublevel P, what is the value of L? L is 1. So ML would have values of minus 1, 0, and plus 1 for a total of how many orbitals? 3 orbitals. We represent these orbitals with boxes. Therefore, a D sublevel has how many boxes? Holding how many total electrons? 10. Okay? The next one is the spin quantum number. Alright? The spin quantum number indicates the direction of spin. How is it spinning? Clockwise or counterclockwise inside the orbital. How do we add that in our boxes? We put arrows. Up arrow, clockwise, down arrow, counterclockwise. Yes or no? Does it make sense? Okay? So indicates the direction or spin of an electron in each orbital. What are the possible values of the spin quantum number? Plus half or minus half. We represent this with an up or a down arrow. Okay? So this whole thing that I have written is the energy diagram that we have. So when n equals 1, L equals 0, ML equals 0, MS can be plus half or minus half. Yes or no? What does that give you? That is your 1s orbital, into which you get 2 electrons. When n equals 2, L can be 0 or L can be 1, which means ML here is 0, but ML here is either plus 1, 0 or minus 1. Alright? And then in each one of this, what is MS? Plus half or minus half? Yes or no? This leads to our 2s orbital, alright? And that leads to our 2p orbital, which can have 2 in each. When n equals 3, L values can be 0, 1, 2. For L equals 0, ML is only 0. For this, ML can be what? Plus 1, 0, minus 1. For this, ML can be 5 different numbers. Is that right? And this gives us the 3s orbital, the 3p orbital, and the 3d orbital. Does that make sense? That's how we get them in the first place. We've been doing it backwards. Does that make sense? Somehow kids, if we do backwards, seem to understand it. But it's actually from the solution is when we write the orbitals. Does that make sense?
Is that on?
Okay. Yes, Ryan.
So how do you determine the value of MS?
MS is just plus half or minus half.
Oh,
It's just for every orbital, it's plus half or minus half, which denotes the 2 electrons, which is a positive spin or a negative spin. Yes. You do questions? Let's do questions. No. It's all recorded, Allah. It's all going to be on blackboard. Okay.
Go back.
It's all going to be on blackboard. We're moving on.
The screen or
So-
the voice?
This the screen and the voice will both be there. Okay.
Okay.
You can probably hear that if you fast forward it. Alright. It won't pick up distant voices. That's why I wear this microphone around me, so that it can pick my voice really well. Alright? You may be able to hear yourself as a very feeble voice in the distance.
Hello.
Okay. Alright.
Hello world, this is Vishnu Room.
Okay. So let's look at this. This is the electron in the 1s orbital. Okay? What are the 4 quantum numbers for this electron? What is the energy level? 1. It is in the s orbital. If it is in the s orbital, what's the value of L? 0. If L is 0, what can ML be? Only 0. Is the electron spinning up or down? Up. So we're going to say it's a plus half. Alright. Let's go to this number and let's assign it quantum numbers. What is the principal energy level? What is the L value? If it's S.
1 or 0. Oh,
If it's S, L is always 0. What is ML? It can only be 0. Because ML depends on L. And is it an up or a down arrow? It's a down arrow. Let's come to this one. What is the energy level?
2.
What is L if the orbital is P?
1 or 0.
Not 1 and 0. P is always 1. Alright. So what are the possible ML values? -1, 0, +1. Or you can it doesn't matter which way you say this. I think last class I said it was -1, 0, +1. Let me keep that consistent. Because they're equal energy orbitals. Is that right? The orientation is X, Y, and Z. So what is this? Let's say it's a +1. It's a down arrow. Therefore, it's a -half.
Why didn't you include the -1 or the 0 in your
For which one? For ML, in a specific, I get the 2S when L is 0. I get the 2P when L is 1. L equals 0 for an S orbital.
Yeah.
L equals 1 and only 1 for a P orbital.
Something conjugates the ML.
The ML depends on L. It goes from -L to +L. So, when it's P, it's -1, 0, +1.
So why did you put -1 in your ML?
These are, remember, P is the 3 orientation. Is that right? We'll just follow by starting with minus and then going to plus.
But I'm just saying, like, when you record it, you only
Because it's here. I decided to label this as +1.
But you could have put it as -1.
Yeah, it doesn't matter. If you label this as +1, 0, -1, it really doesn't matter.
But then would you still put in your ML?
Yeah, it's what you label it.
But you could put it as -1.
Yes, doesn't matter.
Okay.
Yes. Yeah, for P is always L1. Alright, let's do this one. The energy level is 3, L is 1, ML can be what? You can say it's -1, it's an up arrow, let's say it's a +half. Alright, let's do E. What is the energy level? 3. What is the value of L for D? 2. So, if you number -2, -1, 0, +1, +2, what is your ML here? +2. It's an up arrow, it's a +half.
Why is the L for D?
L depends on N, correct? Whenever the orbital is L, L equals S, L equals 0. Whenever the orbital is P, L equals 1. I said D equals 2.
Oh, wait.
Alright? Yes, John. You want to try the next one? Alright, I can't see this one. What is F?
F is 4.
4. L equals?
L equals 1.
Very good. L equals 1. Let's label this 0 plus 1 minus 1. What is your ML?
ML is -1. No,
It can be -1 or 0. I really don't care. What about the spin?
it's got to be -1.
-half. It's a half, not a 1. Yes, Anissa. Which one? ML varies, depends on L. So those are the orientations of the orbitals. Is that right? So the orientations are actually X, Y, and Z. I don't know which of the ones it can go. It can go in X, Y, and Z because it doesn't matter. That is not going to make a difference in its energy. Does it make sense? Okay. Guys, you need to practice quantum numbers, alright? I think I've given an additional practice sheet for homework. Try this and we'll take a quiz next class on quantum numbers. Okay, I'm going to stop recording quantum numbers.